Okay, let's get started. We'll do top hat in the middle of class today. We'll do the middle. So let's get started. We were talking about this rocket basketball problem last time. We had this exact velocity function, rate of change. That was the curve. And you guys built the approximate rate function, right? And that's using constant rates. And those constant rates are trying to be like the exact rate, right? It's a simulation of the exact rate, or a pretend function, like pretending to be that exact rate. And we all need to know 100% confident why we're doing this. Why are we making the rate function worse, right? We've got the perfect rate function. Why are we making it worse? We're making it now approximate and chunky, and it's not right anymore. But there's a really important reason. We all need to know that reason why we're doing that. Where is? Got my list today. Sorry. Where's Kayla Jones? Kayla, why are we doing that? Why are we taking this beautiful, perfect rate of change function, exact rate of change, and making it inaccurate? Why are we doing that? Okay, we already have the exact rate of change, that curve. Then now we're making an approximate rate of change. So why are we doing that? Yes, ma'am. What's that? All right, and we make it out of constant rates of change. Why would we want to do that? Right. So we can go ahead.
So we can determine how much of a quantity we have at every moment.
Right. Okay. So with constant rate of change, we've got some easy math that we've been working on that we can bridge to how much we have, right? How much height do we have of this rocket? By using constant rates of change, we've got what? Given m, or in this case, v, given m, given an m, what? We can take a little change in t and get what? A little change in height, y or h, whatever you want to call it. So given that m, we can take a little change in time. And look, we got a little change in height, a little accumulation of height, right? We're on our way to building a height function. And then from that, we can say that a value of height is an initial value plus change, right? So now if we build up these changes little by little, we can keep track of how much change we have, and now we're building the function for the height or the accumulation. That's why we need constant rate of change, because we've got these principles to help us. Okay, so what was the function? The function was, in the first interval, we're going to choose the left rate, right? R0 for that whole first interval from 0 to 9. And then the next interval from 0.9 to 1.8, we're going to use that actual rate at the left side to be the whole rate. So what's R of 1.5? What's R of 1.5? What's our approximate rate at 1.5? Right here. How would we express the actual or the approximate rate at 1.5? How would you express it? Not R of 0.9. I'm asking what R of 1.5 is. You got the right idea, but it's not R of 0.9. What is it? V of 0.9, right? V of 0.9. Okay? The actual, so we're calling the actual rate V, okay? Or R sub H, R sub H. So V and R sub H, same thing. All right, and so continuing like that, in each interval, we're using the actual velocity or the actual rate of change at the left side, and we just keep going on and on and on like this, okay? So there is our R function, our approximate rate. What? It's based on actual rates at the left side of every interval, and then we let that rate be constant through that interval, and then we choose the next rate. Okay? So what is R of 4? What is R of 4? Where is Jerome Woodman? Where's Jerome? Keeping track. Don't make sure you come to class and answer when I call. Keeping track of who doesn't answer. Where's Christopher Hahn? Yeah. Tell me what's R of, what did I say? 4? What's R of 4? V of 3.6. For every t value from 3.6 to 4.5, the approximate rate we're going to call V of 3.6, a constant rate for that whole interval. Make sense? Okay, so then you've been doing this, you've been building accumulation functions. We've been doing this for about a week. So in that first interval, we're going to take the rate, we're going to use our function for that first interval from 0 to 0.9, which will be what? R of 0. It'll be R of 0 times the change in t, times whatever change in t we have in that first interval. Right? And then what will we do for the second interval? Well, we're going to use the starting height, which is all the height we've accumulated so far, plus the change in height in the second interval. So what's all the height we've accumulated so far? Well, we can actually do this recursively. We can use our a function. What's all the height, according to a, what's all the height that's accumulated up to t equals 0.9? How would we express the accumulated height approximate at t equals 0.9? How would we express that? So easy, it's hard, right? Where's Mark M? Mersh, yeah. How would we express all the approximate accumulated height at t equals 0.9? How would we express that? Okay, where's Catherine Jordan? What do you think? So when we get to t equals 0.9, we pause. We want to know how much, according to the r function, how much height has accumulated. How would we express that? No, that's the rate. That's the rate. Accumulated height. Volunteer, yeah. No, approximate. It's so easy, it's hard, right? I know. I understand. Where's Giovanni? Yeah. No, R is a rate. Accumulated height at 0.9. No, at 0. A of 0.9. A of 0.9. It's all the accumulated height. I told you it's so easy, it's hard, right? Just got to listen to the question. How much? That's our approximate accumulation function. Our approximate accumulation function is A. So if we want to know how much approximate accumulation we've had up to 0.9 seconds, it'll be A of 0.9. So that's where we're going to start for. We're going to start that for interval 2, right? So in interval 2, all along the way, we're going to have a pen that's missing. There we go. All along the way, we're going to have all the accumulation from the first interval plus the accumulated amount in the second interval. So remember, we call this t, comma, say a of t. Okay? And so what? We'll have all that accumulation from the first interval, which we just said was a of 0.9, plus what? We'll have a change in t of t minus 0.9 times the rate. And what's the rate? Well, it's just r of t. Okay? So this is our principle of y initial plus a change in y, right? Y initial in that second interval is everything we've accumulated so far, plus the rate times the change in t. And that will give us all those points right there in that second interval. And then in the third interval, how much have we accumulated now in the first two intervals? It's going to be our starting point in the third interval. How much have we accumulated approximately? A of 1.8. And now we want plus the change in height in that third interval, which will be r of t times t of 1.8. Okay, so look, this is constant rate of change. Rate times the change in t, and then final value of height equals initial plus the change, right? It's all there, stuff we've been working on the last month. Okay, and so we continue on like this, and so we're building this accumulation function. And so on. So at the end of class Friday, we manually found how much height there was at 5, approximate amount at 5 seconds, right? And how do we do that? We just went to the first interval and we took the rate times change in time, plus second interval, rate times change in time. And we got an answer for that, right? So let's just, so all we did was took this Where am I? We took this rate times 0.9 plus this rate times 0.9 plus this rate, right? We're just accumulating the changes at constant rate of change. Plus this rate times 0.9, all the way up to, and then the last interval, what do we have? We just had part of an interval, right? And what was that? We called that, we said that was dt, right? Why? Because dt varies through moments, right? We pick a moment, and then dt varies within a moment. Remember that? So in our current interval is where dt varies. What was our dt? 0.5. So instead of 0.9, dt was 0.5. Okay? And so how did we do it? We added up all the bits of accumulation, mdt plus mdt plus mdt for the completed intervals, and then we had a little more accumulation for this last interval, which was m, which was r of, what, 4.5, not times delta t, 0.9, but now times 0.5, and we got that whole amount of accumulation was what? We came up with a of 5 was 14.28. Anyone have that written down? Yeah. Sound right? Meters. So in this accumulation function, if we plug 5 into this accumulation function, what should we get? What should we get if we plug 5 into this beautiful function I just laid out here? We better get the same thing, right? So we could do it manually like we did it on Friday, or I could take 5 and put it in this function. It should give me that 14.28. So let's talk through that. Yeah. Yeah. Okay, so, and you're watching my recordings, right? I know you are because you asked. All right, so we're going to put in it 5 seconds. So what does this function, so we say, hey function, take care of 5 seconds for us. What does it do? What does it do? We put t equals 5, and what does that function do? I know Jacob knows. Where is, where's Miranda Farraker? Miranda, what's the first thing that function does when we give it an independent value of 5 seconds? Plugs into R. Okay, so where does it go though? Where does it go? Right. Because we gave it 5, it's going to go right here, right? It's going to say, oh, you want the value of 5, so it's going to start right here. Why? Because 5 is between 4.5 and 5.4. And what's it going to do? Then it's going to put 5 here. It's going to take a of 4.5 plus what? R of 5 times 5 minus 4.5. So look. What's the 5 minus 4.5 represent? dt. Okay, so we now change in something is not specific enough, right? Because we've got moments, delta t's, and we have dt. So just to say a change, we got to be more specific now. So which change is this? This is dt, right? This is the amount of change in the current interval, dt. So that ends up being 0.5, right? That was our 0.5. Times what? R of 5, which is, we come over here, R of 5 is V of 4.5, good, right? Because that's that constant rate in that interval. So what is all that together? R of 5 times 4.5 is what principal, or what is that right there? dy or dh, right? The change in height for the current interval. And then what are we going to do? We're going to add it to all the height that's accumulated before at 4.5. And then how would we get that? Now it's a of 4.5. What do we do with that? Right. So yeah, to process a of 4.5, we're really asking a of 4.5. It comes up here, and it takes 4.5 and puts it in here. It finds that total amount of change in that interval, plus all the accumulated changes in the previous interval, see? And it just keeps working back. So we won't take the time to do that, but if we were to work all that out, we would get 14.28. We'd get 14.28. But this is called a recursive definition, It's using all the accumulated change in all the previous intervals to build the next interval, the current interval, right? So in any particular line, it's building the total accumulated change for the current interval, this part, plus all the change for the completed intervals. So that's what we talked about, right? Completed intervals. How's that represented in this function? A of 4.5. A of 4.5 is all the accumulation for the completed intervals. And then this is our little m dt, which is the little bit more change for the current interval. It's this part right here. And what do we have? Y initial plus the change in y gives me final y. You see how everything we worked on, all the pre-calculus stuff that we emphasized, it's all involved here. That's why we tried to say you've got to retain everything. Everything's going to play an important role altogether. Questions on this? So this is the last time we're going to do one of these. Why? Because what happens if we wanted this function for 100 seconds? What was that a function going to be like? Extremely long. We're going to have some, 0.9 seconds, more than 100 lines, right? More than 100 lines, like this. Or what if so many of you know that to make our rate function more accurate and our approximate accumulation more accurate, we're going to do what? We're going to take smaller intervals. That's a very intuitive thing. Many of you have already foreseen that. Then what happens to AT when we take smaller intervals? More and more lines, okay? So this is great in principle. It's great for understanding, but yuck, right? It's going to get long and tedious. So here's where we're going to start today. We want to make this a function in one rule. We want one rule that takes care of as many separate interval rules as we want to have. 100, 1,000, 1,000,000. Okay? So we're going to have one rule instead of a separate rule for every interval. We want to build this function that's going to do the same thing in one rule. Okay, but in principle, understanding this is crucially important because it's the foundation of how we build accumulation from constant rates. So you still, absolutely, even though we're going to build a much more efficient version, this needs to make perfect sense, and you need to be able to create these and interpret them and use them. Okay? All right. So that brings us to the animation that you studied. So we got to have all these pieces of this animation, that terminology and what things are called down pat. So that brings us to that and top hat. Here we go. Why do we show it? Why do we show it as an animation? Why? Because displayed graphs came about. They were generated, right? As two quantities change together, the graph is formed, one correspondence point at a time, right? That's what graphs are about. When you see a static graph, you see this thing that looks like a wire or a stick. It's not a wire or a stick. It was formed when two quantities changed together, one correspondence point at a time. Okay, super important. And that's why we keep showing you the animation like that, because that's the image, the powerful image you need to have of a graph. Okay, so what kind of graph is this? Like on that y-axis, what kind of unit would we have? Rate of change, right? Rate of change. We got two kinds of rate of change graphs there, right? The red one is exact. Wrong way. Something like R sub f, where f would be the true accumulation function. So it's that rate for the true accumulation function f. Okay? And the black one is? Which we just call just plain old R. It's our approximate rate of change. So the red curve, exact rate of change. The black, constant rates, is our approximate rate of change. We know that's essential to have constant rates of change in order to build accumulation, right? dy equals m dx. And y final equals y initial plus a change in y, right? We use those principles to start with rate and build accumulation. Okay, so what is that black increasing quantity at the bottom? Just x, right? Just x. Right? X is measured from the y-axis, right? It's shown as a distance from the y-axis, and that's why that's showing all the way back there. So one thing we haven't talked about yet is Over there at the left, you see a value of A. A is going to be reserved for where we're going to start accumulating from. We don't always have to start at 0. Okay, so in most examples we've seen, we started accumulating at 0, but we could start anywhere. So the value of A is going to stand for that X value where we're going to start accumulating. Okay, so that's new. All right, but then X is then how far into the intervals we've gone in terms of just it's the current value of the independent quantity, right? It's the current value of our independent quantity. What's next? How about, let's do the blue next. The blue next. No, let's do the purple next here. So these double purple, what is that signifying? These double purple question marks. Completed. Got the right one, just wrong way. Okay, those are the completed intervals, right? Been there, done that. Already calculated the accumulation for those completed intervals. All right. What's the double gold? What do we call that? That's the current interval. That's right. That's where the action's happening, right? So that's where we're seeing the increase in x through the current interval. Okay. And so then in the current interval, what is that blue question mark? That is up here. Right. Right. What did we say? We said dx is the amount of change in the current moment, right? In the current moment, and that's a variable. That's a variable. So it starts here, and then so it varies from what to what in this animation. Dx varies from what to what? Okay, but what values, right? Dx is an amount of change, so it varies from what to what? Dx. Where's Patrick Yoon? Patrick. Aiden, go ahead. Yep, in this case, 0 to 1.5. Do you see that? That it's 1.5 now, it starts over 0. And then it's increasing to 1.5 because it's the change. It's not the value of x all the way back to the y-axis. It's the change. So in this scenario, dx is varying between 0 and 1.5. And what's 1.5 called? That's our delta x, right? And I could have shown that on any one of the completed intervals, not just the last one that's completed. But as a value, that's clearly delta x. But it could be, I could be showing delta x from here to here, from here to here. All of these are delta x. That's our fixed moment width. It's the width of a moment, delta x. Did we get all 7? Okay, so as we're building this, our goal now is to build the one-line accumulation function in one line. And so we got to have all these mechanics around the rate function solid. So does all this make sense? All this terminology, all this, these quantities, do they make sense before we get into starting to build the one-line accumulation function, which is not a simple, easy task. But we have all the tools. We just need to do it a little bit at a time, and we can do it. But this needs to be in place. Stuff coming up. Turn your brains on. Turn your brains on. Everything that we've seen is going to come into play here. We know how fast the value is changing at every moment. What's that? How do we know that? What kind of rate of change function? It starts with an exact rate of change function. And in the end, we want to know how much of the quantity we have. And what's that? In the end, we want to know how much of the quantity we have. That's a? So what we're after is an exact accumulation function, but we still have to build the one-line approximate accumulation function first. So how much we have is accumulation. So here's a familiar diagram or image. We just saw it. And so I'm going to say A is going to start somewhere here, just past 2. We don't know what that value is, but we're going to start accumulating at 2 point something. And now the current value of x is 6 point something. The current value of x is 6 point something. So again, imagine this thing emerging, but we have to kind of pause it to make sense of a given situation to build it. But don't ever lose that image of x value increasing, constant rate function in steps emerging as x increases, right? Okay, so what do we want to know? So how much do we have at x equals 6.75? Current value of x. 6.75. Based on the approximate rate function, how much do we have? So In general, how would we do that? Just in general, how would we come up with how much we have at x equals 6.5 given what we've done? How would we do that? So just a very general strategy for getting the amount that we have at x equals 6.75. I'm sure, I think Aiden probably knows. Somebody else? Just a general strategy. What would that be? So we're going to use all this stuff that we're talking about. Where's Ciara? Ciara B. Yeah. So just very broadly, just how are we going to get how much we have at 6.75, like in the big picture of it? What are we going to do? Well, we're trying to figure out what the A function is. So what did we do like with the basketball situation? What did we do with the basketball situation? Yeah. So are you looking, oh boy, what happened? Oh, good. Okay, so you started here. No, that's great. You started by talking about this over here. Yeah. And you said you wanted to get the change in y for the current interval. And then she said after that you want to do what? Okay, so completed intervals are not a quantity, right? That's an object. So we want to add. We don't want to add it to the completed intervals. We want to add it to what? All the changes or all the accumulated amounts from each completed interval. Okay, that's exactly right. We've got to add up all the change from the completed intervals plus the change from the current interval. Okay, so what does that look like? Rate times change in x plus, what is a rate times a change in x? It's a change in y. That's what this whole thing is going to be based on. So what does this represent? Right there. R times the change in x. That's our first completed interval, right? That would be the amount of change from the first completed interval. And then what's this? The amount of change from the second completed interval, right? Rate times change in x plus rate times change in x, and that would be the change from third plus rate times change in x. But that's the smaller for this only the part of the current interval. That's why it's dx there at the end, right? Nothing hard about that. We're just summing up changes. Each change we get by m dx. dy equals m dx. Or in this case, completed intervals would be delta x because that's the width of a moment. Okay, so how would I express the rate in the first interval? How would I express the rate for that first interval? What is this constant rate right here? Don't estimate, but I want it exactly. How would I express that rate from the first interval? Where is Peter Hernandez? Peter, I want to express the rate for the first interval. This one right here. How do I do that? So where does that rate come from? That rate comes from what? The actual rate where? R of A. That's it. It comes from the actual rate at the left side of the interval. Oh, right. We talked about this already. We want change from completed intervals plus change from current interval, right? So that's just a little. Okay, here we go. So change that first rate as R sub A. What is R of 3? What is, oh, sorry. Yeah. What is R of 3? Should actually put, we're going to put R of F's here. These should be RFs. Okay, so what is R of 3? What is R of 3? What's our approximate rate at x equals 3? Where is Brandon Bills? How would I express R of 3? Brandon. Yeah. I want to express The approximate rate at x equals 3. R of 3. What is it? R sub f of a. Right. So it's that rate at the left side, R sub f of a. Okay, good. Now, how do I express the constant rate in the second interval? I don't know what this x value is, but I want to express it exactly. So how do I express, it's going to be R sub f of what to get this constant rate here in the second interval? I know these two know. Anybody else volunteer? Yes. Right, look, because we want a plus 1 change in x. So this x value right here is, what is that x value right there? A plus, so remember we can't say change anymore because we got to either say delta x or dx. Two different varieties of change. So we want a plus the change of 1 moment gets us what? To the left side of the second interval. So that's what we're going to plug into RF to get that constant rate for the second interval. Okay? What about the left side of the third interval? What is that x value? Right there. What's the left side of the third interval? Yeah. Right. So to get to the left side of the third interval, we need to go across 2 intervals, right? We go across 2 intervals. That gets us to the left side of the third interval. So a plus 2 delta x. Okay, and did you hear that? So this is a key point. To get to the left side of the third interval, we have to go across 2 intervals. Key point. We're about to see this because we have to generalize that. To get to the left side of the third interval, we go across 2 intervals. Does it make sense? Okay, and then what about the current interval? Current interval starts at what x value? Easy, right? Now that we got the pattern going. A plus. To get to the start of the current interval, we have to go across how many of the completed intervals? To get to the start of the third interval, we go across how many of the completed intervals? And how many of the completed intervals is that? What's that? All of them. To get to the left side of the current interval, we're going to go what? Across all of the completed intervals. That takes us to the left side of the current interval. Yes, sir? No. Yeah, and I don't want to get, that needs to be R. Yeah, that needs to be R, okay? And a little bit of a can of worms. Love to talk about it later, okay? But yeah, so that's going to be R. The other ones are R sub F, okay? All right, so what we want to do then is what? Notice how all these terms for the completed intervals look a lot alike. We're adding a lot of things together that look a lot alike. And how can we represent that instead of writing it over and over and over again? Right, we're going to use the summation notation, right? So it's our friend, it's not our enemy, right? It's not the scary thing, it's our friend. It allows us to express when we're summing the same thing over and over and over again with just a subtle change, right? And so we can just write it once. And it shows the principle that we're doing. What? We're summing up what is each R delta X. What is each one of those? What is R delta X or M delta X? A change in accumulation, right? A little bit of accumulation. And how do things accumulate? Bit by bit by bit by bit. A little change at a time. So this notation is representing exactly what we should understand, that we're summing up a bunch of changes. Each change we get by M times change in X. M delta X. Okay? So now the only difference is then, and then what we say, we're going to start with so J is going to be the interval number. J is going to be the interval number. We're going to start with the first interval. We're going to stop at the third interval because there's 3 complete intervals in this scenario, right? So the only difference between these things that we're adding together is the value of the independent variable. Again, this is R sub F, the complete intervals, R sub F, okay? So the only difference between each of those terms is what do we plug into the R sub f function? Okay, and we've already started doing that. Look, so we just got to figure out what is our general form for the left side of each completed interval. So the j, we want to start with j equals 1. That's really convenient because then j stands for which interval we're in. Okay, so r sub a times delta x, interval number 1. So j equals 1. So we know that these can start at 0, but it's a little more intuitive to start at 1 because then that j stands for the interval number. So when j is 2, interval number 2. When j is 3, interval number 3. Okay. So what did we say? We said to get to the left side of any interval, say the third interval, to get to the left side of the third interval, so j equals 3, how many complete intervals do we have to go across? 2. To get to the, say we had 18 completed intervals. To get to the left side of the 18th completed interval, how many completed intervals would we have to get across to get to the 18th? 17. So we're always going to have what? We're always going to have A. We're going to start from A, and we're going to add how many completed intervals are we going to add for the jth interval? How many completed intervals are we going to add for the jth interval? Good. So can you write out what we should plug into R? Can you write out what we should plug into R? So in other words, what's the x value at the left side of the jth interval? What's the x value at the left side of the jth interval? Where's Zishu? Zishu U. Zoo. Zishu Zoo. Okay, how about Munzer? Where's Munzer? Charlie. Where's Charlie? Okay, what's the x value at the left side of the jth interval? We're going to start at A, and we're going to go across how many intervals? J minus 1. So how do we express then the x that's got all the information we need to express the left side of the jth interval? What would it be? Volunteer, Jacob.
Would it be A plus J minus 1?
A plus J minus 1? So close. What else does he need? Yeah.
He requires parentheses around the J minus 1.
But still missing something. Yes, sir. A plus J minus 1 delta x's. Right? A, start at A, add J minus 1 delta x's. So it looks like that. A plus, where we go to get to the left side of the jth interval, we're going to do J minus 1 delta x's to get there. All right, so that's going to go right there. And so now we've got a nice compact expression for the sum, all the accumulation for the completed intervals. And it doesn't matter how many we have. It doesn't change the length of this. Right? If we have 1,000 completed intervals, the only thing that changes is what? The final value of j, right? The final value of j. Just the 3 would become 1,000. So it's no more writing. Okay? So, here we go. What is this? We're summing up. So you got to see the big picture first and foremost. That it's the sum of lots of changes, right? Each change is found by, back in the day, we called it m dx. And that was so easy, right? It just, the constant rate times a change in x gave us a change in y. Well, now the only difference now is that we're going to sum a bunch of those up. In this case, how many are we summing up? 3. But if we wanted to sum up 1,000, then what would be the only change? Yeah, then that would just be 1,000, right? So what if there's 1,000 completed intervals? See how handy that summation notation is? Instead of having 1,000 lines in our accumulation function, okay? So this now gets us what? The total change, sum of the change of the changes from the completed intervals. Okay? And so then next time we'll work on this a little bit. So then there's a little bit more, right? There's a little bit of change from the current interval. That's what we'll work on Wednesday. There may be a little bit more added. Check black.